In Chapter 6, we learned how to compare two population means based on two independent samples, and we used t-test to do this. In Chapter 7, we look at also a one-way ANOVA method, meaning that one-way ANOVA meaning that we have one variable that has multiple levels, and that's very often times referred to as treatment. And so we'll have now then t treatments or groups, and this value of t can be 2 or greater. Under the assumptions of normality, we can look at analysis of variance. A non-parametric alternative, non-parametric meaning no parametric distribution assumed. A non-parametric alternative is the Kruskal-Wallis test. The Kruskal-Wallis test is based on ranking the data from 1 at the lowest score to the highest score in the entire sample. And so therefore, since we need to understand this concept of ranking, this seemed like a good place to put a procedure that ranks data. The GLM procedure stands for General Linear Model. The GLM procedure has been around for a number of years and is one of the most common SAS procedures that performs an analysis of variance. It has a great deal of utility beyond analysis of variance, and so we're just going to learn some of the basics here. So to get an analysis of variance test, there are actually 3 of the 4 statements written here that are required to do what we need it to do. The first is the proc-GLM statement, the second is the class statement, and the third is the model statement. Those 3 have to be present if we're going to generate an analysis of variance. Additionally, we can ask for these means to be requested, so we could regard this mean statement as an optional statement. And then the note here, we could have optional statements for by and where the previous rules for a by statement apply. That is, the data are sorted in a compatible manner with the by statement here, and a where statement where we can specify what conditions must be met by the data in order for that data to be included in this analysis. In addition to specifying the data set on the proc-GLM statement, there are several options that are available, and so I have some of those listed here. We look for the possibility of some ODS graphics here, and so you can suppress all those graphics, and it likes to generate a couple of box plots. And then there are also options on a model statement and on the mean statement we don't talk too much about. I do mention some alternatives on the mean statement, but the model statement, I don't mention those here. If you have some advanced background in looking at analysis of variance and performing these kinds of analyses, then you can check the SAS help and documentation for available options there. For the mean statement, that generates the sample mean for each of the T treatment groups or T treatment levels, and so we can get confidence limits for the means and can specify the alpha associated with those confidence intervals as options to the mean statement. Those of you with some background beyond just the beginning statistics class may also know some things about multiple comparisons procedures, such as Tukey's honest significant difference, Fisher's least significant difference, Bonferroni methods, and others. To illustrate how an analysis of variance can be done, we'll consider this following example that comes from Meat Science. In Meat Science, treatments that improve the quality of cooked meat are investigated. In this experiment, there is a control group denoted by capital C and 2 experimental treatments denoted by T1 and T2 applied to cuts of beef prior to commercial packaging. Similar steaks are independently assigned to each of the 3 treatment groups. After cooking the steaks by the same method to the same internal temperature, pH and cook yield are measured on each steak. There are 5 independently treated steaks in each treatment group, and these data appear in Table 7.2. So treatments are C, T1, and T2, and then we have pH and cook yield measured, 2 response variables measured for each of the steaks. So in Objective 1, we want to create the data set meat from this table, and compare the response means for the 3 treatment groups by conducting an analysis of variance at the 0.05 level. And so if we have anything going on, we can clear it, and then we data set meet, and where we have group, pH, and cook yield. Group is followed by a space and a $sign here because these are alphabetic characters, and then pH and cook yield are numeric. Cook yield appeared as 2 different words in the above table, but it's written here as one word. That is, that space in the middle has been eliminated in order for it to satisfy the SAS naming conventions for a variable. And here's how it looks in SAS. You could have used the double trailing at for the cursor control if you wanted the data to read across. Typically when we start getting multiple or more columns in our data sets, I usually recommend not to do that. We can generate this analysis without plots simply by using the plots equals none, which was objective 7.2, and then we can look at the residuals. We have to put the only here because the wants to generate the box plots, and if we only want to look at the residuals and diagnostics, it's the plots only. And then down here we can include the confidence limits for the means. I'll put those uppercase here. Now we'll do this run this because this is a little different than what's stated in the book. When I just run the mean statement with the one variable, I got the mean and the standard deviations, and so we have to pick up actually another method. So one of the easiest things to do is compute the least significant difference, and then it'll generate the confidence limits for us. So that's a little quirky. Okay, so it gives us information up here about making pairwise comparisons, but if you want the confidence intervals for the individual group means, you have to select one of those methods: Tukey, LSD, Bonferroni, etc. When the data sets are not normally distributed, or rather there's a lot unknown about them, one of the alternative methods is a rank sum test method, and whenever we have more than 2 treatment groups, it's called a Kruskal-Wallis test, and it's a chi-square test statistic that we compute, and it's rejected for large values of chi-square. There's also one for just when there's 2 different groups, and this is referred to as a Wilcoxon rank sum test. So if you need to review those from an earlier methods book, I encourage you to do that. But they're both based on ranking the data. So to make the method work, all of the observations are put in order and ranked from 1 at the smallest to the largest, assigning average ranks when there's ties, and then we compute the test statistic based on the rank sum. So each one of these add up all the ranks for group 1, all the ranks for group 2, and those are the RI values here, or the rank sums. We also use the rank sum for the first group here to compute a z-score in this Wilcoxon rank sum test. This is two of the tests that the NPAR one-way procedure in SAS does. So those execution steps for computing the test statistic for these methods are just above. Here we have NPAR one-way, so that is a 1 in the middle of this word, and we have our data set requires a class statement. The class statement serves to identify the populations that are being compared. NPAR one-way does not have a model statement, but it uses a VAR statement, and so that we won't have response equals a treatment there. It'll say only what the responses are for the particular group variable in the class statement. Now the NPAR one-way procedure will generate up to 9 different non-parametric tests and 1 parametric. It'll generate the analysis of variance, so in these options we can specify what it is we want. The only 2 we're really talking about here today are the analysis of variance and the rank sum tests. So here are the options for that NPAR one-way statement: ANOVA and Wilcoxon. So it's Wilcoxon if we want the ranked sum test, and if we have more than two treatment groups, it's going to be the Kruskal-Wallis test. And then it also has a list of plots that it likes to draw for both analysis of variance and for the Wilcoxon box plot. Other non-parametric methods not overviewed here are specified here, but if we don't put any options on NPAR one way, we're going to get all of these. Like the previous procedures, by and where statements can be inserted in here for the NPAR one-way procedure. So if you want NPAR one-way calculations done for multiple levels of a variable, you requires a by statement. If you want to exclude some data from this procedure, then you can do that for using a where statement. And so we'll demonstrate this with a where statement. We could have done this in some of our earlier methods as well, but in Objective 7.4 is what we'll look at next. In Objective 7.4, we want to use the MEET data set that we created in Objective 7.1 and compare the distribution of pH for only the control in the T1 group using non-parametric rank sum methods. And we want to use alpha equals 0.05 in our conclusions. So if we're only going to use rank sum methods, that means we want the Wilcoxon method here, no ANOVA, none of the other scores. We want to exclude T2, so group not equal T2, so that means the other groups are going to be kept in this. So this statement keeps all of group T2 in the MEET data set, but just excludes it in this analysis. Then we look at group. It's going to have two levels, control and T1, and the responses here then are going to be for the pH response. Objective 7.4 here, Wilcoxon scores or rank sum scores for the pH variable. So what's going on here? Then it gives us the sum of it ranks the data as we discussed. Average scores were used when there were ties or average ranks, and so that it gives us what the sums of the scores are. So since we have a 0.5 in here, there's likely a tie then. We can do a two sample test. This is that Wilcoxon rank sum test, and so there are one-sided and two-sided alternatives there, and so we're just looking at two-sided. Are they the same or are they different? And so right here, this 0.6004, this says then that these two groups are not different whenever we use a Wilcoxon approach. Kruskal-Wallis is the chi-square statistic, and it can be computed when there's only two groups also. It is a different statistic than what's being computed up here, so you do get a different p-value for that. And so by either one of these tests, then we would decide that these are two values, our groups are not different with respect to their pH response variable. Using our alpha equals 0.05, we're comparing that. Both of these p-values are well in excess of 0.05. You can request the box plots to be suppressed for the Wilcoxon scores if you wanted to, and so that here it's just puts in that test statistic for two groups here, but these are the sum of the ranks. Pardon me, the distribution of the ranks, not the sum of the ranks. In the analysis of cook yield, we don't need to exclude the T2 group, and so notice here there's no where statement in this one. I've asked NPAR one way for both the Wilcoxon and the ANOVA test, and I've asked not to draw any plots. And so it could be that we needed to excuse the T2 on the pH analysis for other reasons. If we didn't need any exclusions up here on pH, we could have put both variable cook yield and pH in the variable statement here, and we would have gotten the complete analysis on both of the responses. So in Objective 7.5, first the analysis of variance. We can see that this is the same information we got out of GLM for cook yield. It labels cook yield here in the header of this table, so you have to look for it to find out where it's at. Similarly, you could review the output in the previous objective for pH. Wilcoxon scores for cook yield right here again. So it gives me then these three groups. I don't get that 2-sample Wilcoxon rank sum test table that we got for pH because there are three groups, and so the sum of the ranks are given here, the 19, 51, and 50. If they were all equal to each other, we'd expect all those to add up to 40. So we're looking for some departure there, and so here we get something a little bit different at 0.0365 than we get in the analysis of variance. They are two different procedures, and so the problem is, say, if your data are not normally distributed, is this method up here picking up actually the difference in the non-normal from one group to the next? Is it picking up that non-normality, or is it picking up unequal variances, whereas this down here is not being influenced by the distribution? Again, here you'd want to review some of your methods from your introductory statistics. That's oftentimes where we'll see rank sums introduced for the first time, and so it'd be a good idea to review those in addition to the analysis of variance before picking these up and working with them much further. The NPAR one-way procedure used ranks for the data. It didn't print those ranks anywhere, but including the rank procedure in this chapter seemed like a good idea to me. So I have proc rank. Which data set do you wish to rank? And then there are options here, and some of these options are really less of options and more like things that you really need to do. What variables do you wish to rank? You can rank one or more variables in the same procedure. You need to assign to those variables in this the ranks. What are they going to represent? So if you have variables x, y, and z up here, then you need a rank for x, a rank for y, and a rank for z. The order you specify here in the VAR statement, same order specified in the rank statement, and that way you can identify what the ranks are, and you can examine the ranks or examine the initial variables or both. Now, while they are listed as options for proc rank, I said I regard them not as options. You need to create a data set where an original data set it will be contained and the newly created ranks that you've just named in a rank statement. It will automatically rank each variable in ascending order unless you say otherwise. And so that if you want things in descending order from largest to smallest, then you will need to specify that. When observations are tied, how do you want that handled? Do you want the ties equals mean? Do you want it to be the high number or the low number? And so especially once you start doing ascending and descending and what's high and what's low and those connotations, we need to look at very carefully the output we get. The VAR statement, as I told you before, we can rank one variable or we can rank multiple variables all in the same procedure. Just list the variables you need in the VAR statement. Now then the procedure, if you use the descending option, that means every variable in the VAR statement will be ranked in descending order. If you want some in ascending and some in descending order, depending upon your application, you would need at least two rank procedures to do that. And we spoke about the rank statement, so we must have it in addition to the variable statement so that we know what the variable name is for the ranks that we're creating. In Objective 7.6, we have 3 columns of data. We just generically labeled those as X, Y, and Z, and they have 5 observations each. And I've picked these out so that to illustrate a few points here, since there's only 5 observations. Here we have 5 distinct values for X. For the Y value, we have 2 25s or a tie there, and in the Z column there is a 3-way tie. So how are those handled? So this is data set 6, and we want to rank the items in data set 6. We're ranking all 3 variables. We're putting the results, the data being ranked, and the rank variables in this new 6 SAS data set. Our ranks, I'm choosing RX, RY, and RZ because R for rank and then X, and so which order those go together. It's easy to tell at a glance. The rank procedure, a couple of notes here. The rank procedure only produces a SAS data set. It does not produce any printed output. So if I want to see these ranks, I'm going to have to print the contents of data set new 6. So that's why I have a print procedure here. The other thing is notice that it's going to rank things without the use of a sort procedure, so I don't have to sort things in order. The rank procedure is going to work on things appropriately without sorting the data. So if the data are entered in any sort of a meaningful order, we don't need to change that for proc rank. So I have here this data set 6 and the rank procedure. Okay, so here down at the bottom of our results viewer, my original data set X, Y, and Z, and then I have the ranks of each of those. We may have decided that a better thing to do would be to print X and then its rank right next to it, and then print Y and its rank next to it. That might look even a little better, so let's see if we can do that and maybe make that look a little bit better. So the print procedure, we can say X, then its rank, Y, then its rank, Z, then its rank. So I like that, the look of that perhaps a little better. Alright, it's the same information, just the columns are reordered. So here I had no ties. The 47 is the lowest score, it's 1. Quick scan, 89 was the highest score, it got rank 5. In the Ys, I just caught that typographical error and brought it over from the book. Excuse me. This should be rank of Y. Let's try it again. There we go. So our lowest score is 25. Okay, and it's in positions 1 and 2, so therefore the positions held are 1 and 2. The average rank is 1.5. Then the next highest score is 27, and it's in the 3rd position, then 4, then 5. So you can see how the average rank works there. The Z scores, I have this 3-way tie for 37, which is in the middle. 29 is our low score with a 1, and then in positions 2, 3, and 4 it's 37. So if I average 2, 3, and 4, I get a 3, so that's why they are given rank 3. And then we have a 5 here for the highest. In Objective 7.7, we're asked to experiment with this dataset 6 and create first investigate maybe what's going on with ties equals high or doing things in descending order. So if we just do ties equals high here alone, and we've got the correction on the print, so make sure and mark that correction in your textbook, please. And so that this is the ties equals high. If I don't do anything to the tie here at 25, instead of averaging 1 and 2, it gave us the higher number and put in the 2s. For the 3-way tie at 37s, instead of averaging 2, 3, and 4, it put in the highest value of 4. So ties equals low, then would do just the opposite of this. And then you could also look at what's going on whenever it says descending. So those would be some options then additionally for you to check out. In Objective 7.8, we're to rank the X observations in ascending order and the Y observations in descending order in a new SAS data set named 8. Z will not be ranked. print the data set 8 in ascending order according to X along with the associated ranks. Use only one print procedure. So there's a couple of different options we can do this. In the first option, we can look at our, because we have one is in ascending order, X's are ranked in ascending order, so I want to rank X in ascending order. Y's are ranked in descending order, and so I have a 6A and a 6B data sets that are created. And then I can sort each of those by values of X and Y. They both have those in common. And then in data set 8, I merge the created data set 6A and 6B by the XY pairs they have in common. And then we can print that information. Okay, so this is the option 1, and I could again put the ranks next to the variables, but I've got the ranks on the ends here. We sorted things in ascending order by rank, so you could either sort by X or sort by the rank of X to get ascending order for that variable. The other variables then won't follow any sort of order, but they'll be ordered according to X. So in this option, we had two intermediate data sets that we had to sort and then merge together. How could I avoid doing that? So if we come down to option 2, we can still put our ascending ranked X's in a data set called new 6. Then I take new 6 and pull it in, and it's going to be the data sets that's going to be ranked, because new 6 has all of the things data set 6 has in it, plus the new ranks for X. So if I pull this new 6 in here, and then I can evaluate the Y's and output those to a data set 8, and I can put my descending modifier on there for the ranks of Y's. If we want to print things out in order for X, we still need to either sort by X or sort by its rank prior to printing. And here I change the order of the statements of the variables in the VAR statement. So I got the ranks right next to it, so you can see the X's now are in ascending order. Z was not ranked. Well, so we have the same information as option 1, just a different way of doing things. So ranking data is important. How many times do we hear the weather person say the coldest day all year, the coldest day all month? Or when we look at our sports teams, we want to know who's doing the best with respect to a certain stat that's being kept on the teams. And so those of you in class are probably already can kind of see where some of this is going with regard to some of our practice and assignments that you've been getting. That's all for these right now. We'll pick up again in Chapter 8 with learning how to in-file data.